Hit record. So yes, happy Thursday. Happy that I was overly cautious on Tuesday and worrying about the storms. Happy to be wrong about that. But there are quite a few people in the Coralville and Iowa City area who have damage and problems, and so I wanted to be sensitive in case any of you were in that situation. Happy to be back here and have everyone okay, as far as I know. Let's see. So things that are happening. This is the part of the semester where I'm starting to lose my marbles, so stay with me here. Forgive me a little bit of what is going on. As you notice, I'm back to 7-Up, so that's your key as to how caffeinated I already am. We are doing formative assessment, the last one, I think, in this class. And another thing that I did yesterday while I was trying to get organized was update the syllabus for this class, the written version that you can save as a PDF in case you ever need to show it to somebody. And I was just laughing as I looked at this because I was way off. I was so far off in my estimation as to how much we could carve into one semester. But as I was looking at it, another thing I noticed is that I had decided to give each formative assessment 3 points instead of 2 at the beginning of the semester, and then never did that. So you all get 3 extra points added to your scores just because I forgot to do that. So right now I've added 2, and then after the third, you'll get the third. So up to 9 points from formative assessments in this class, which I had done because I figured that they would be more difficult than relative to some of the other classes that are worth 2. So like, what's a logit is a very different question than describe how time-varying predictors should be modeled in longitudinal data. So an increasing level of difficulty deserves increasing points. Another thing that I updated on the syllabus on Tuesday, I need to start class at 12:50 instead of 12:30 because I'm involved in a 3-day departmental review process where I have to be in meetings all day, and otherwise I'm not going to get lunch. And you don't want me if I haven't had lunch, okay? Just trust me on this. So that I can make sure that I can fit all of those meetings in and still get to class, it'll be 12:50. So my plan for Tuesday then is to go over the formative assessment and then turn things over to our first presenter. Thank you for being willing to go first so that we have plenty of time for that. So just to remind you of what the rubric says with respect to the presentations, because you guys are taking over the show for the next couple of weeks. I'm excited to see what you've been working on. You will have 15 to 17 minutes for the presentation itself. And then I'm expecting 6 to 8 minutes for questions and discussion after that. And I've allowed 5 to 10 minutes, I think, with that total for the changeover in terms of making sure to get up to the presentation computer. Please email me or send me a link to where I can download your presentation file in whatever format you want to use it by 10 o'clock on the day of your presentation. I will make sure that it is loaded up on my laptop. Because of all of the connections in terms of the Zoomers and the recorders and everything, I can't have you switch your laptops in and out. It will just take too much time. So plan to present from this podium. Also, because we're still maintaining a hybrid environment, plan to stand in front of this podium. I know that when people give presentations, they kind of like to walk around, and it's easy to sort of turn around and gesture manually to the screen. The Zoomers cannot see that. So get used to using the mouse so that it gets picked up on the screen as well. And on that note, I'm going to share the screen. So Zoomers, I have the rubric open. That's what we're looking at here. In terms of time limit, I am going to be strict with you because number one rule when you give a presentation at a conference or a job talk, you do not go over time. It is disrespectful and it makes it look like you weren't planful. So I will give you, I think, probably like a 2-minute warning when you're about out of time. I'll be sitting somewhere in the corners here, and I will cut you off if you go over. So my advice is to underplan, like don't shove all the slides in. A 15-minute presentation is maybe 15 slides. You also don't have to make a slide for everything. You can just stand and talk. You can stand and explain, the background of your story. You don't have to have whole sentences of words up there or even bullet points. As I mentioned before, the story that you're telling is not necessarily just the most direct path to what you ended up presenting, because that's not going to be as beneficial to your peers. So what I would like you to include, like number 8 here on the list, preliminary analyses. How did you decide which variables needed to show change versus fluctuation? How did you evaluate Whether or not longitudinal invariance was going to hold in order to do factor level change. What blind alleys did you go down, right? Like, I started out trying to do it this way, I ran into this problem, and here's how I fixed the problem. Those kinds of troubleshooting things that you wouldn't normally put in a presentation, I think are appropriate for this context. So in order to make time for that, I would expect the introduction portion of this to be relatively short. So in terms of what this would look like for a conference, normally this part would be a little longer, the results would be more streamlined. I'm asking for the opposite. More detail in the analysis and the choices that you made, a little less detail on the theoretical basis for your study, which most of us are not necessarily going to appreciate anyway. We just need to understand enough to appreciate your research questions and a little bit about why this is important. So these are the things that I'm looking for. I'm going to be trying to take notes myself as this is going on, and then I will give you feedback later. Your job also is to give feedback to each other. So on the schedule, each person is assigned as a peer reviewer of someone else's presentation. Those are going to be due the Wednesday of the following week. So people who are presenting next week, those peer reviews are due next Wednesday, and so on for the next 3 weeks. If this doesn't go well, so if for whatever reason I decide you don't get full credit on this, I think this is worth 20 points, you are allowed to revise by recording your presentation again and sending me a link to where I can view it. So that is an unusual thing, because normally when you give a talk, it's your one shot, but I believe in the opportunity to learn from your feedback and try to improve. So you are welcome to re-record, submit me a video somehow that I can watch by the end of finals week for potential to get full credit. The peer review is worth 5 points as well, and you are to email it directly to the student that you observed. Try to be positive, yet not like, it was great. That's not a peer review, right? Here are some great things I liked about it. Here are some suggestions I have for how you might approach this in the future. Balanced criticism. I know that all of you are probably a little nervous about this. It's easy to be nervous. I hope that we can all be constructive and learn from each other. So I'm looking forward to seeing these, honestly. It's going to be like a parent watching a recital where you're playing piano or you're dancing or something for everybody. Except you're going to be modeling, Well, not the kind where you walk around on a catwalk with fancy clothes on, but, showing off the modeling. All right. Any questions on presentations or procedure or what to expect? All right, I have tried to make it so that each peer reviewer will be at least in town on the days where the person is presenting, but all these are planning to be recorded, and I will post them somewhere where you can access it. That way, if you are a peer reviewer, you can rewatch the presentation if you need to revisit parts of it. So that's also unique to this situation. Normally, those aren't recorded. Yeah, I think that's it. So whatever we don't get through in class today, I will make a video to finish, but then I'm done talking for quite a while, until the last week of class. One other thing that I did put up on the course website yesterday to try and give you some resources for things that we did not get to in this class, I put up a Word document that has resources for intensive longitudinal data as well as for location scale mixed effects models. And some of this is my stuff. So for instance, I have a class in 2018 where I did a couple examples with this. I have a bunch of references in the Annual Review of Psychology article I wrote about multi-level models that was published last year. I have a YouTube tutorial by Don Hedeker that I found. The most recent episode, I think maybe 2 weeks ago, of the Quantitude podcast had Ellen Hamaker as a guest, who is a big person in the world of intensive longitudinal data and dynamic structural equation models in particular. So her discussion with them, I think, is a good entry point into these models, and they have a whole bunch of references and links to her videos and things that you can watch about that as well. I also noted that last fall's series of the APA free trainings, there was a 3-part video series about intensive longitudinal data, beginning with sort of design and then continuing with analysis, and so I think those would be useful as well. And then last but not least, I do have an example using SAS in a previous class where I did a 3-level model of occasions within days, within people, which T is going to tell us about, I think, next week as well? No, the week after. Okay, week after. I don't have your schedule memorized. I just know who's going first. That's all. Yeah. So these are some additional resources for the things that I didn't get a chance to do. The last week of class, what I had planned on doing is designs in which people are clustered, and it's longitudinal as well. So there's a couple of you who are working on that as a type of project, but I wanted to cover that a little bit more formally. And just as a heads up, in the fall, I am teaching the clustered version of multi-level models. If you haven't had that, that will be a useful complement, I think, to this course. Because it's clustered data, it goes a lot faster. I can get through more extensions because time takes up so much time. So I will be doing, for instance, generalized models in that class, so longitudinal model or models predicting binary outcomes or count outcomes. I also have crossed examples in that class, so cross classification, like subjects and items, explanatory IRT model connections, that kind of stuff. So extensions in terms of the multi-level modeling world that I wasn't able to get to this semester. So I need a third semester of this class. I need 3 to get it all done, but I can't get there. All right, any questions on any of that?
Oh, I have a question about the peer review emails.
Yes.
So when we email the person directly, should we CC you?
Yes, send it to both of us, because I'm going to be grading you on your peer review, and I want them to have your feedback. So yes, it's not anonymous. You all know who is reviewing each other, so keep that in mind, I guess. None of you is going to be reviewer 2, right? We're all going to be nice to each other and constructive. I'm quite certain of that. Any other questions about this? All right, then I'll shut this down, and we'll talk about multivariate change. How's that? So we left off on, I think, slide 18, 19 last time. I think that may be a good spot to start. So the objective here, whenever we have time-varying predictors that themselves show individual differences in change, then we have to model it that way. So step 1 in contemplating an analysis with multiple repeated measures, each of which could potentially have individual change over time, is to figure out for each variable what you need. So if it shows change as a question, what kind of change is the second question? And the way that you would approach this is exactly what we did last semester. So saturated means is step 1. Find a way to estimate per occasion means so that you can plot them and figure out what kind of trajectory you might need, whether it's linear, quadratic, piecewise, latent basis for stuff that's a little bit weird, or if you only have 3 or 4 occasions in which a second slope is not going to be estimable. Different ways of doing that in terms of the software, but it's a critical step. If you're able to do so, check out the pattern of variance over time. If the variances change over time, that's a giveaway that you need some kind of random change slope. So where you can go back to person mean centering would be a situation where you have fixed change over time, but not random. It's the individual differences in change that are the big difference, because that represents a third source of variation that we have to care about. If it's just fixed change, controlling for time as a regular covariate will solve that problem. Residual variances over time. It is an empirical question, the extent to which these might need to be separate. However, you won't see that unless you're in wide data SEM. Otherwise, if it's just the within model, it doesn't distinguish what the variability is at each occasion. And there's not an easy way to ask it to do that. And residual covariances, also potentially in the wide model. Second, then, is to try to put everything all back together again. So once you've settled on what type of growth trajectory you would need or not need for each outcome, so if the time-varying predictor has individual differences in change, that's where it needs to be included as an outcome. And your choices are single-level structural equation modeling or multi-level structural equation modeling. Both of these are multivariate models in which you can predict more than one column. You could substitute person mean centering, any kind of observed variable centering, if it only has fixed change. So that's the thing, is that if you just stick time in the model, then you've solved that problem, because the time-varying predictor's slope will be after controlling for time, which will be the part that's left over. The debate then would be whether or not you should move to latent centering anyway and just have a random intercept. I think that's usually better, but it depends on how much information you have. If you're working with a small sample, this may be more than what you can reasonably expect from the data. So then at level 2, it's up to you how you relate your intercept and change slope factors. You can have them just covary. You can have one predict the other. Just have a caveat here in terms of prediction. I think it makes the most sense if you're going to have a predictor of another variable's change to also have that same predictor on its intercept, because that's like the main effect is the idea. And having it predict change is like having the predictor by time interaction. So from a linear model's perspective, this would make sense. Then the question is, what do these paths represent? Are they between person relationships, or are they contextual relationships, which is the relationship after controlling for any level 1 prediction? And that is the tricky part with these models. So I have a table here. This is in my 2019 paper that I wrote because I was so mad that I had to figure this out. And this table was actually suggested by some colleagues. I had given them a draft of my paper to read, and they were like drowning in all the words. Like, can you just make a table? Like, that is a really great idea. So thank you, RDA, from the University of Kansas, for this suggestion. But this is my estimation of what happens under various different scenarios. So in terms of the terminology in this table, the first column here describes whether you have fixed effects or fixed and random effects, and whether the variable, how it's centered. So this first section here is univariate MLM, so like if you're using EMLR or mixed or something. And then it's pretty straightforward because it just depends on what kind of level 1 variable you have. If you took out the between level variance, then you know that the level 2 slope is going to be between. If you didn't take out the level 2 variance from your time varying predictor, you know that the level 2 slope is contextual because you set it up that way. Where the ambiguity comes in is with respect to different ways of multivariate models and where the slope is specified. So I have an example that illustrates this, but just to try to put it into general terms first. So if I have a within level latent variable, so I let it deviate up my time varying predictor into random intercept variance that's like the person mean, and residual variance that's like the within person deviation. So it's the analog of person mean centering. And I ask for a relationship between X and Y at level 1 in the level 1 model directly. So level 1 direct here is just like doing this, Y on X in the level 1 model. Then the level 2 result is between. If I have an uncentered observed variable, it follows the same rules as it does in univariate MLM because it's being treated the exact same way. If I have a within level variable that is latent centered, and I have a fixed effect only, so note these two are the same model except they're specified differently. This potentially could give you different outcomes. This is with Bayesian estimation. They're both between. But if it's ML, then one's contextual and one is between. So the placeholder notation as it's referred to here is level 1 slope is the name of the slope that is being treated as a latent variable in the model. So the relationship between two variables itself, the slope, is a latent variable in this analysis. So then its mean and variance would go in the level 2 model instead. So it's two different ways of asking for the same relationship. The latter way allows you to add a random slope to it, a variance around this slope, as well as cross-level interactions. All right, so the example I have has some combination of all of this to work through. But let me make sure I got all the lines here, I think. Yeah, I think so. Okay, I feel like I'm missing one, but this is the whole table, so we'll have to see. So here's some troubleshooting tips so that you know what you got, because the only way that I figured this out is because I was using simulated data where I know what the answer should be. So my first recommendation is to start with the simplified model in which each outcome is predicted by only one thing at a time. That way you can track down like what its relationship would be without worrying about whether it changed because it was a unique effect versus a bivariate effect. So this problem of whether your level 2 model gives you between or contextual slopes is only relevant when you have relationships at both levels. So like if I have x's, if I have a model for x where I have an intercept, a change slope, intercept factor, change factor, and a residual, and I have the same thing for y, if the x predicts y within persons in the level 1 model, that's when this is relevant. If this isn't here, it's going to be between. So in this case, some of the level 2 relationships could become contextual instead of between. Here's how I would recommend checking. You can estimate one model in which you have a level 1 relationship between the residuals of x and the residuals of y and a fixed slope. So use the direct specification, and then compare that to an alternative model in which this is a covariance instead. So an M plus A would be an on, and B would be a with. They should, in theory, fit the same, right? Because you have a direct relationship between those two pairs. So if any of the level 2 slopes changed across these two versions of the model, then they're contextual. Because they should not change. If they change, it's because in A, they're controlling for this level 1 relationship, whereas if it's phrased as a covariance, they don't. So that would be my advice in practice, is to fit these two versions and see what happens. And you should be able to get linear combinations of the two in that case. So you should be able to add the contextual and within slopes together to get to what the between would be in Model B. Okay, questions so far? And by the way, the M+ manual is completely silent on this issue. They absolutely do not interpret these things in any way, shape, or form. All of this has come from people who are trying to figure out what the hell is happening under the scenes, like me, and the extent to which we can try to convey it. So Chris Preacher, in some of his multi-level SEM stuff, has his supplemental materials have like some of this discussion on them as well. So he's the only other person that I've seen who's gone to the trouble to try and explain this. You have a bunch of articles on your reading list, too, that are talking about multi-level SEM and mediation and relationships of this type. So in wide data, then. Okay, question first. Yeah, please.
So, two models, you do your level 1 relationship as a with statement.
Mm-hmm.
As a covariance. Then you look at the effect that's in your between level and you write it down.
Mm-hmm.
And then you estimate the next model where your level 1 relationship is using an on statement.
Yes.
For the fixed slope, or for the directed path.
Mm-hmm.
And then you run that, you take what's in your between output and write that down.
Yes.
If those two numbers are different, then what you're estimating is contextual effect.
That is exactly right. So I'm going to repeat what you said for the benefit of the recording. So you listed the steps in a different order, but it doesn't matter. So if you start with a covariance at level 1 between two variables, write down what the between model gives you. Paste it into a Word document or something. Or save it as a different name, since we have like 8,000 output files at this point, right? Just don't call any of them final. Just do not use that word. You're going to jinx yourself. So level 1 relationship as a covariance. Write down what happens in the between model. Then make it a slope instead. See what the between model says. If it's the same, the between model is between. If it changed, the between model has to be contextual, because it's now controlling for the level 1 relationship. It only controls when it's phrased as a regression, not a covariance. So all of this is predicated on the idea of the multi-level version of this estimation, where you're using long data. If you're using wide data instead, you have the same concerns. So in wide data, if you have the box from an X predict the box of a Y at the same occasion directly, what you're going to get in the level 2 model will be at least partially contextual. The way to fix it is something that's called a structured residual. It goes by different names, but that's the one that I see most commonly, and I think that term was coined by Patrick Curran, if I'm not mistaken. What he does, and I'll show you how to do this in code, is to move the residual variance that's supposed to represent within-person information after controlling for an intercept or a slope, whatever you need, and move its variance to a new latent variable. Then from an estimation perspective, this variable only contains within variance, and so the path that it takes to your outcome then is only within, and the level 2 model becomes between. Otherwise, if it contains the original variable and the path is going that way, then it's like it's controlled for level 1 and all of this is contextual. So it's the same idea as in person mean centering versus grand mean centering. Moving the variance to a new variable makes it look like person mean centering, whereas if you don't, it's in the original variable that has all the levels, then it becomes a contextual effect at level 2. So this is a neat trick. The problem is that, at least as far as I can tell, there's no way to allow potential random slopes for this path in structural residuals or cross-level interaction type things. It becomes very onerous because from an estimation perspective, it thinks you have all these additional latent variables. This would also not be possible for generalized outcomes in which residual variance is not a thing. The newest addition to M+, which is not in my example because I think it requires 8, and I'm not sure if that's what we have, is a caret symbol, the thing that's above the 6, like a hat. In their code, you can use that hat thing and not have to literally make another variable. And I believe that that translates into limited information estimation for binary or ordinal outcomes as well. So under WLSMV, I think you can use the hat thing. That's a new trick that they've incorporated.
Lisa, that I found out that if you do use weighted least squares multivariate, you have to use Bayes as an estimator. You can't use maximum likelihood with that caret thing.
Okay, good to know. Yeah, it's in so there's an article on your reading list that's called Residual SEM or something simple like that, and it has what you can do and not do. So this is a trick that you can use, but it doesn't work in all situations. Otherwise, you can just ask for a linear combination and then get your between back from within plus contextual if you don't use structured residuals. All right, so how are we doing? Okay enough? All right, I want to keep moving through this slide deck rather than switch to the example because I don't know how long the example is going to take. And however it takes, I'll record the rest of it in my basement. So this is one situation in which you would use a multivariate growth model, is to examine the extent to which the intercepts of one outcome predict the change of another, or the change predicts the change predicts the intercept, however you want to do it. Residual relationships. If I'm off my line today in a positive direction on X, am I off my line today in a positive direction on Y? Or am I off my line today, then what happens tomorrow on Y, like a lagged relationship? Within persons is only a lagged effects are logically within persons. Some other types of models that use this same premise, where we have both X and Y having its variance partitioned by the model into intercepts, residuals, and potentially change slopes, is in rescuing a curve of factors model that fell apart. So a few of you might be in this situation. In example 3, like 2 months ago, you might remember this, we did a curve of factors model. And so in that model, what you do is first start with a latent factor that describes multiple outcomes at the same occasion. So the outcomes are supposed to be indicators of a single latent trait. You put all those together for separate occasions. Hopefully longitudinal invariance holds, and if it does, then you can examine the extent to which that common latent factor changes over time. So we did that with a latent basis model for 4 occasions, I think 3 indicators, 4 occasions. And the purpose of doing this type of analysis is when you believe, like each of these indicators by itself is not a good representation of my trait, you put them together, you should get a more reliable measure of whatever you're trying to study. And I want to know if that more reliable thing itself changes over time. So you're thinking about this, even though it's a multivariate model, you're thinking about it in a univariate kind of way. Like in example 3, I had a latent variable called cognition, and it was measured by abstract reasoning, memory, and processing speed. So my question was, does cognition change over time? Like one thing. But this requires at least partial longitudinal invariance, meaning that the relationship between the indicators and the latent trait stays reasonably the same over time. If it doesn't, here's plan B. Factor of curves model. And it took me many years to remember which is which, because these sound like they should be synonyms, and they are not. In this model, the order of what's higher versus lower is backwards. So the lower order factors, first step is to estimate a growth model for each indicator. So in that case, I'd have a growth model for block design, a growth model for abstract or processing speed, a growth model for memory. Second step then is to estimate regular latent variables, not growthy kinds, but just regular kinds, to see to what extent the relationships among the intercepts across indicators could be described by a common factor, like common intercept, and then the extent to which the relationships among the changes could be described by a common thing. So this allows you to answer the question like, do these indicators change similarly over time in terms of the correlation patterns? Like if I start out higher than everyone else on reasoning, do I start out higher than everyone else on memory, on processing speed? If I change more on one, do I change more on the other? Are the patterns of correlation among these things consistent with the idea of a higher order factor? This does not require longitudinal invariance, and it does not require that all the outcomes change the same way. So here are some pictures to show the difference that I stole from our readings. So the first one, this is what we did in example 3. This is curve of factors. So I have in this picture 3 indicators of my latent trait. I have 4 occasions worth of latent traits, and then I have squiggly 1 and squiggly 2, which I would call intercept and change. And the patterns of loadings on here is how you can tell what this is. Whenever you see 1s on all the loadings, that's an intercept. Whenever you see something like 0, 1, 2, 3, and that corresponds to which occasion is which, there's an implicit path here that should have a line with a 0 on it. This is some kind of change factor. And it's linear change based on the fact that it's 0, 1, 2, 3. The opposite is on the bottom here. So this picture down here is factor of curves instead. So the lower order models here, this is from another article on your reading list. This is an intercept factor. This is a change factor for X, intercept and change for Y, intercept and change for Z. So the pattern on the change factor here is ambiguous. If you fix them to constants, you could create linear or piecewise or what have you. If you estimated the loadings, you could create latent basis, in which you'd have to fix 2 of them and estimate the others. So then at this stage, the first thing I would do is just see if these are correlated. Just fit a model in which all the intercepts and slopes get to be correlated however they want. If they have consistent patterns of correlation, then it would be reasonable to see to what extent they're in common. So this higher order factor here has a 1 to identify it, to give it a scale, and then 2 regular factor loadings here. This one that they've labeled FS for slope or for change has a 1 and 2 regular loadings as well. So these are not change factors up here. These are common factors. Their job is to reproduce the covariances among the intercepts on the bottom and among the change factors on the bottom, in the same way that a measurement model is designed to reproduce the covariances among the indicators. So at this stage, the intercepts and lower order slopes are like indicators of common intercept and common change in this model. Question?
Sorry, I'm having trouble seeing it. So it's a
tiny.
1 and a lambda for each of the higher orders?
Yes.
Indicating like a 1 and an asterisk and an asterisk?
Yes. Yes, this is a 1 asterisk asterisk. And this is the marker item method of identifying these higher order factors. Alternatively, if you fixed each of their variances to 1 to identify them, then you'd have a star, star, star for all 3 loadings. It's either one. So the change stuff is happening on the bottom. The extent to which it's in common is happening on the top. In the other model, the common is on the bottom and the change is on the top. I'll say that again. In the bottom model here, factor of curves, the change is on the bottom and the common is on the top. In the one we did in example 3 on the top here, the common is on the bottom and the change is on the top. So it's 2 different things. But longitudinal invariance is required for the top one. It is not required for the bottom one because you're not making one factor in the bottom. Question?
Yes, if we're using the indicator the marker item option for our factor of curves, I understand that this one in the factor of 0, that higher order term, yes, that's for the variance, right? We are setting down the factor loading to 1 to estimate the variance.
The variance of the higher order
Of the
factor.
higher order factor.
Yes.
What about the mean in that case? The factor mean is taking the factor mean of that lower order?
That's what it looks like is happening. Even I can't read the font that's this small. But it would be the same situation where either you would estimate the means down here and fix these to 0, or you could estimate this and, fix this to 0 and bring it up here. Same premise.
Right.
Yeah, these are just regular common factors, but their indicators are these things down here. So I believe at least one of you is going to have this as a project, so you'll get to see an example of what this looks like. All right, other questions or any of that you want me to repeat? So this type of model is extraordinarily complex. I can't see it being particularly useful other than to make the point of whether these intercepts have something in common and these slopes have something in common. But theoretically, you would then have predictors like boxes out here predicting this general intercept or this general slope. So, all right, so that's number 2, ways that people would use multivariate growth models. Cross-lagged relation is number 3 here. So within person relationships we've examined up to this point have been concurrent. So most of the time it's like if X is higher than usual today, is Y higher than usual today? But they don't have to be. So if you're interested in lagged effects, like yesterday's X predict tomorrow's Y or vice versa, you can do that in univariate MLM, and I had an example from my friend's dissertation where we had stress predicting psoriasis in one of the slide decks. But you can't go both ways. In those sorts of models, you can person mean center X and create a lagged version of it, but Y is a latent variable. You don't have access to it to be able to stick it in the data set from the previous occasion. So you can examine lagged relationships in one direction, and you can only do so after dropping the first occasion, which is sort of a bummer. So people generally tend to move to a multivariate framework when they're interested in what's known as cross-lagged, where it's X to Y and Y to X and potentially other variables as well. In this case, we would use typically wide format SEM to do this, because that way you can have lags that are like 2 apart, 3 apart, however many you want. The more recent version of multi-level SEM that's known as dynamic SEM has this kind of feature as well. So dynamic SEM incorporates time series types of parameters, including autoregressive effects and cross-lagged effects for previous occasions, which are stored on a different row of data. So that creates additional sources of difficulty, particularly if you don't have complete occasions. Like if the times are uneven, it has to figure out like what the lag would be, even if I don't have yesterday and I only have the day before, that kind of thing. The same issues in terms of not wanting to smush between and within together are relevant here, but they're not as easily appreciated or as often appreciated in wide data SEM. So here's some examples of what not to do. So these are examples of things that are still far too common. So I just want to point those out as what to watch for. It's not an exclusive or exhaustive list by any stretch of the imagination. So there are other kinds of models that I am deliberately not showing because I don't like them. They are known as accumulating models, and you can read about them in these papers right here. The reason I don't like them is because they don't have a clean separation of between versus within. They're sort of muddied together in a way that I think makes the interpretation of the parameters very, very difficult. But they are out there, so I wanted to give you some resources in which you can learn about those. So the big picture is that if you're seeing a wide SEM longitudinal model and you're not seeing latent variables that differentiate their sources of between-person variation, that model is smushed. So here's an example. This is what's known as an autoregressive cross-lag panel model. It's either abbreviated ARCL or CLPM, depending on who you read, and it needs to go away. There's a lovely article about this that you can read. It was published in Child Development, so it's very understandable. Admittedly, I was reviewer 1, so this article has a little bit of my influence in it, but I thought they did a really nice job, and I'm happy that it's done well. So the logic of this type of model is that, well, we're going to control for person dependency via these paths within the same variable. So y1 to y2, y2 to y3, etc. This is what's known as an autoregressive path. Then we have like y1 to x2 and x1 to y2. This thing is the cross-lag path. So when I talk about this, you'll see me make this gesture because that's what it looks like. These are the autoregressives and these are the crosses. And by tradition, the first occasion of each variable gets to just be correlated, and the residuals at the same occasion, that's what these arrows going into it are supposed to represent, get to be correlated as well. And sometimes, but not necessarily, they hold all of these slopes to be the same number, all of these slopes to be the same number, and then constraints to make those go the same way as well. So the problem is that this idea of controlling for the previous occasion via an autoregressive path is insufficient. Now, do you remember, like a long, long time ago when we talked about R matrix models, alternative covariant structure models, and the AR1 model? The AR1 model says that the correlation between y1 and y2 is b2. To get from y1 to y3, the correlation is b2 squared, cubed, fourthed, fifth, and that makes the predicted relationship follow this exponential pattern of decay that states that if you go far enough out in time, there is no relationship between y1 and like y10. That's not going to hold. In most longitudinal data, occasions from the same person have at least some constant correlation to them, no matter how far apart in time. So this model is assuming that doesn't happen, and it's also not assuming that there's any individual differences in change. So both of those things have to be absent for this to be valid. The intercept being absent is particularly the problem. So each of these cross-lagged paths is smushed. We don't know whether it reflects constant mean differences that were there to begin with, changes, or within-person fluctuations around projected trajectories. That's the problem. This model is a longitudinal mediation model that suffers from the exact same problem. So in this case, we have sort of not cross-lagged, but it's directional. So we have the x to the mediator, and then the mediator to the y, but without intercepts and slopes. All of these paths are also smushed. So this also doesn't give enough opportunity for different types of mediation to play out, because you can potentially have between-person mediation involving intercept differences, change slope differences, residual differences, and so forth. So here are some ways to fix these. This is what is known as the random intercept cross-lag panel model. It has gotten a ton of attention. I have a list of articles you can read about this that's published on the MPLUS website. But the key idea is I'm going to allow intercept differences in both of my variables here. So note the ones. That's how I know that this is an intercept. The intercept factors in these models are almost always covaried rather than predicted, but that's a choice because the interest is in the bottom part here, and this is the idea of structured residuals. So the residual for x has its own separate latent variable in the code. The residual for y has its own. So I would have to write out 10 different latent variables here and then specify the autoregressive and cross-lag interaction or paths between the residual parts. And if you forget that, if you write code that says like x0 predicts x1 and x0 predicts y1, you do not get the same thing. That turns it into an accumulating model instead. So the structured residuals is important to getting this right. I did not realize that at first, but it is. So this is an alternative that a lot of people will be like, I know cross-lag panel model is bad, so I'm going to do this one. What kind of individual differences does this model assume, though? Main differences. Where'd change go? What if x has individual differences in change over time and y does? That's in here. So these paths down here are going to be some smushed combination of what the within-person relationship would be and whatever relationship there is that's not in the model between the change slope for x and the change slope for y. That's a distinct kind of smushing that you can see. So, random intercept cross-leg panel model is designed for fluctuation kinds of outcomes. It is not designed for change outcomes. So whether or not you need a change factor is always an empirical question that you would want to examine first before fitting everything in the same model like that. I have a paper that's under review right now that is looking at this in more depth. And one of the things that I found when I was playing with simulated data is that I could fit the smushed version of this model without the random intercepts or the random intercept version, and I could get excellent model fit and not realize there was a problem. Because these paths can all compensate for each other to some extent, even if they're not reflecting the true mechanism. So model fit is not necessarily an indicator that everything is okay. So here's what it would look like if you added the change factors. This model has a bunch of different names. I believe it is tied to this source as the first place. Latent curve model with structured residuals, multivariate growth model with structured residuals. It has like the first part, it depends on who wrote the paper, what it's called, but the structured residuals part is this part right here. So the difference is that now we've differentiated intercepts and change slope. In the between-person model up here, you can have these things correlate or predict each other as you wish, and then the within-person model is where the autoregressive cross-lag effects are. Logically speaking, that's what should make sense. Because when you think about the idea of a lagged effect, like what happened this time predicts something next time, that's a within-person idea. Because if it reflected constant person mean differences, why would we care if it is this time versus next time? Like I'm the same person the whole time. So this type of model, I think, is much more in line theoretically with what people are thinking about when they think about lagged effects, in addition to being unsmushed. If you don't want to do structured residuals, you can still do this, except that then these things up here are contextual. So that's the benefit of going to the trouble of the structured residuals. Lagged effects in long data are possible in M+ starting in about 8.1, which was a couple of years ago. But the first version of it is something you should not use. It is still in their manual, which is why I am highlighting it here. So this y on y ampersand 1 versus y on y caret 1. The difference is in what the lagged variable contains. So in each of these, this is a coding system that allows you to take like the previous occasion and have it predict the current occasion where they're stored on separate rows of data in a long format data set. In the original version, when they first came out with it, it was the whole y at the previous occasion. So it created a smushed lagged effect, even if the current part of the model was specified correctly. In the new version, it is the lagged effect of the latent centered predictor instead. So the lagged effect of the within person part of the predictor, as it should be. So this is a relatively newer way of doing it, and this would be a better choice. All of these things are only available using Bayesian estimation, however. And here's some sources on that. Finally, last but not least, what about longitudinal mediation? Here's an example of what one can do. So this is a paper that I helped with former colleagues at the University of Nebraska, where they were looking at anger and effortful control as measured at 54 months, which is age 4.5, I think, if I'm doing the math correctly. So right before you would start kindergarten. And then they have growth trajectories during elementary school for teacher-child conflict, intercept, and change, teacher-reported externalizing behavior, intercept, and change, and then mother-reported externalizing behavior, intercept, and change. And so in this level 2 model, these are time invariant predictors because they were only measured, these two traits were only measured at this occasion with respect to this analysis. And they were interested in the extent to which, say, effortful control as a young child led to teacher-child conflict in kindergarten, and then maybe that was responsible for greater externalizing behavior in terms of where it was at kindergarten, also change. So the black lines in here were the things that were significant, and I forget which indirect effects were significant, but as you can see, there's a whole lot of different possibilities as you sort through these things. So I have 3 different variables that each have their own growth curve to them, various patterns of direct effects from X. These were conceptualized as the M's, and these are the Y's. Now, some folks would say, hey, but the intercept is measured at all the same time, and that doesn't count as mediation, and I say, sure, because mediation is supposed to be the idea that something is causing something which takes time to happen. So can you think of an idea that I could potentially address that criticism if reviewer 2 was mad at me about that? You can't call it mediation if all these intercepts are at the same occasion?
Change the intercept for the Y.
Yeah, change Y. Nothing's stopping me from taking this time metric for these outcomes and turning it back around so that time 0 is like 8th grade or whatever. Then you have temporal precedence, and that gives you, I think, maybe a stronger leg to stand on. So it's up to you how you set up the models. At the within-person model, though, can I talk about mediation if I have teacher conflict residual at the same grade, teacher conflict residual at the prior grade, and then teacher-reported externalizing, mother-reported externalizing, so these are lagged within-person effects among the mediators and the outcomes? I can't talk about that. What am I missing? Let's talk about mediation. I don't have an X. Could I have had an X? According to the way I have these variables set up here? No, I don't have one. These are time invariant. So I would need to have an X that is measured at multiple occasions in order to have the within-person part of X join the little within-person model down here. So one of the fights that I had to have with reviewers to get this study published was that they wanted to have all of the mediation cross-laggy stuff in the same model. Note that these are directional and only one direction only. The reason that I wanted to do that is right here. Me personally, this is an unpopular hypothesis. Let me go back to this picture here. The fact that the same occasion residuals are only correlated bothers me, because the paths going from previous to current are not controlled for the current relationship. And I feel like if you're going to say that it was last time that matters, then you need to show that last time predicts incrementally above this time. That's my own personal opinion. It's unpopular. But in this paper, we had 2 different versions of the model in terms of which way the within paths went. That way we would control for contemporaneous and a directional pattern. And it worked out that there was stronger evidence in favor of one than the other. In favor and in flavor, as it were. So it got published eventually, but it was a contentious battle with reviewers to do so. So there's my conclusions. Cheers. How are we doing? Want to see an example? Or at least part of an example?
Yes, please.
Question?
Yes, please.
Yes, please. Oh, yes, please, a question, or yes, please, example?
Yes, please, example.
Okay, yes. A lot of abstract words. So this is an old example that I've given multiple versions of over the years, and I changed it yet again to give this version because I realized that the language in here was god-awful. Here's the situation. I got in the habit of saying like intercept and slope, like a long time ago, and that's how a lot of you are talking to, because what do you mean when you say intercept and slope? What does slope mean? Change, right? Well, at this point, I have a latent factor for change in one variable. So time is the predictor of the outcome. So the latent variable represents a slope. And this other latent variable represents a slope. So I have int slope, int slope. But then I have a path connecting them. So this is the slope to the slope. And this is the slope to the slope to the slope. And those words are not synonyms. So I tried to change this so that I was only using slope to describe the path, because paths are slopes. And I'm using the word change where I would have said time slope. So I've got int and change, because I figured like that would be a little bit cleaner. So if you see any places where I missed it, I apologize. I tried to go through all the M+ code with a fine-tooth comb as well as this handout to try and get all of those things fixed. But I figured I would try to make it a little bit more understandable. So this is simulated data, which is how I would have only figured out what the heck was going on. It is based on a true story, though. So this is based on some data at Penn State, where I'm looking at risky behavior in adolescent girls. So here's a spaghetti plot for what this looks like. Parental monitoring in adolescent girls at the same occasions. And then here is risky by monitoring. So the x-axis on the first plot and the second plot here is age, because it was simulated to be relatively balanced, and everybody started around 12. And it looks like risky behavior is increasing over time, and indeed it is. So in Chapter 7, I built the unconditional models for these outcomes, which was fixed quadratic random linear with respect to risky behavior. Monitoring I made as fixed linear is flat. But do you see the pattern here? Changing variance? That's a dead giveaway that there are random slopes in here. So some girls are having their parental monitoring decreasing across age, and some girls are having it increase. And then this is, irrespective of what age it is, a spaghetti plot where I'm predicting monitoring and risky behavior. So I know what the true answers are in terms of how monitoring and risky behavior relate to each other. And I will show you the answers here in just a second. So here's the first model. I have written out as an equation because the first model is a correlated intercept and change factor model and correlated residual model. This is the kind of model, if all of your relationships across your variance components are specified as covariances, that you can do in univariate software. So you can trick SAS Mixed or Elmer into doing these sorts of models. Basically what you would have is a G matrix that has 4 random effects, intercept, change, let them all just be correlated, and then a within person time-specific R matrix where each variable gets a separate residual variance and you can have a covariance between them as well. So I specified this as an undirected model first just so that we could look at the correlations across variables and know what to expect. So this is an undirected multivariate MLM. All of the output and input files for this example are online for you. Since it's fake data, you can have that. So this is long form data to start with, and then the next version of it will be in wide form. So I've answered a number of questions about M+ code, so I think it's worth going over this in a little bit more detail. In the model, use variables include time and time squared, which are my predictors, attitude 4, which means parental attitudes about smoking and drinking and other bad things, which is a time invariant predictor centered at a score of 4 out of 5, risky behavior, which is my time varying Y, and parental monitoring centered at 3 on a 1 to 5 scale, which is my time varying X. So even though I'm going to let it divvy up the variability in monitoring, I am still centering it so that 0 is going to mean something in risky behavior. Otherwise, the risky intercept would be for somebody with a monitoring score of 0, which could not happen given the scale of the state variable. Then these things. Folks have emailed me who have forgotten this, and their model did not converge as a result. If you have a variable that is only on one level and you don't want it to divvy up its variance, that's what these lines are for. So attitude 4 is a time invariant predictor that is only going to go into the between model as an observed variable. Likewise, time and time squared are observed variables that only go into the within model. If I forget this, then M+ will try to figure out how much of the time variance is at level 2 and how much of it is level 1, and that's not going to go well because time doesn't have any level 2 variance. I have a 2-level model here with random slopes. I'm using regular flavor ML. An option would be MLR if you have outcomes that are potentially not normally distributed, but I made up these data so I know that they are. Here's my within model. So I've got the residual variances, which would be in the R matrix here. I've got 3 placeholders. So I have linear and quadratic change for time predicting risky behavior, linear change only predicting monitoring, and then I have a covariance between the level 1 part of each of these variables. So because the relationship between monitoring as my X and risky as my Y is a covariance, that means all of this stuff is between, no questions asked. That's the one that's like, okay, I've got this one. I only have a fixed quadratic for risky behavior. So R quad here has a mean in the brackets, but it does not have a variance. I shut it off. So I have 4 fixed effects here, actually 5. Fixed intercept, fixed linear change, fixed quadratic change, and fixed intercept for the other variable. These are the intercept variances at level 2. These are the change variances, linear change. Then we have my time invariant predictor on intercept and change. Covariances between intercept and change. And then we have the cross ones. So this is within variables, and these 4 are between variables. Then I made correlations, because M+ doesn't do standardized results in these models, only in certain combinations, but never with random slopes. So model constraint is a way that you can ask M+ to do math for you. So for instance, you can ask it to make an intercept correlation. You can ask it to make an interclass correlation. You can ask it to make simple slopes within interaction terms, or model implied mean differences for alternative groups, that kind of thing. So I have rescore, intcore, lincore, which to me is level 1 correlation among the residuals, intercept correlation, and then linear change correlation. And then these are the cross, let's see, RIS, MIS. This is risky intercept slope, and then monitoring intercept slope, and then intercept to, I need more characters here, but you only get 8. That's why these names are so terrible. And then I just ask for it using the labels up above. So I labeled all the covariances in the G matrix. I also labeled all of the variances in the G matrix. I labeled the residual variances in the R matrix, the residual covariance in the R matrix, so that I could do math down here. And the formula for a correlation is covariance over the standard deviations of the 2 variables. And so then I just used all the labels to make myself some correlations. So I'm doing this to help recreate the total relationship between these variables will be the same if I can standardize it in this kind of way, regardless of after I change it into slopes. I just want to get a sense of how related these things are. Okay. Any questions on any of that code? All right. Survey says, so all of my output here is unstandardized. for the purposes of our example, I'm not caring about the affective attitudes. I'm going to be caring about these three numbers. So I simulated these results to have this pattern. This is what I was going for. There is a negative relationship between the intercepts, and in this model, it is at age 18 is where the intercept is, because I figured that would be where the most variation is in risky behavior. So intercept correlation that is negative 0.46 means that girls who have higher risky behavior at 18 have lower monitoring at 18. The Lin core here, as I've called it, is the correlation between the two change slopes. Girls who grew more in risky behavior over time either grew less or maybe went down in monitoring. So I have to be careful in the way that I phrase these things. Let me go back to the pictures. Risky behavior looks like it's increasing for everybody over time. And I could compute a random effects confidence interval around the fixed effect to try to describe like what the range of individual slopes would be. So I can talk about what it means to be high on change versus low on change. According to this picture, somebody who is low on change means that their slope is less steep or maybe flat, but they're still potentially going up. Whereas in this picture, some people are going down and some people are going up. So it's harder to talk about what being low or high is if change is potentially in multiple directions at once. But the idea would be there's an inverse relationship. People whose parents decrease their monitoring over time are children who increase their risky behavior over time. So like the idea of the level 2 model here was paying attention to what your kids are getting into is good. So there's an inverse relationship at level 2. At level 1, there's a positive relationship instead. If you are being monitored more than usual, your risky behavior is higher than usual, higher than predicted. That's what I was going for. Maybe you are rebelling, right? Maybe mom's all up in your grill and you decide to teach her a lesson. Or maybe mom finds some pot in your room and she cracks down on you. Right? Either way, no causality here, but it is possible to have a level 1 relationship that's different than the level 2. So that was what created the story. Here is that exact same model if you were doing wide SEM instead. There are, let's see, first thing I had to do, switch the data from long to wide. Have you seen T-scores yet? Have we done that in this class? Okay, good. I was thinking we hadn't. That's why I wanted to put it in here. So I have a variable that's called like occasion in the data set, which is approximately the way they were measured, but it was uneven. So in order to account for that unbalance, I have a variable that I'm creating that is the exact age they were measured, centered at 18. That age-specific set of columns is going to be used in this command right here for T-scores. What T-scores does is I come over here to my picture and say my risky slope right here, this is change over time. If I wanted to have the intercept at time 0 right here, this would be 0. This loading would be for the change slope. And then this would be like -1, -2, -3. But locking these down into integers assumes perfectly balanced data. So what T-scores does is tell M+ to say, hey, instead of making this -1 because it's the occasion before, use the value of exactly how far before it was for each person. So it's individually varying factor loadings here is what T-scores is creating. That's how you would allow for unbalanced time. If you had balanced time, it would look like this instead, where you would just lock down the loadings into integers. I guess you could use decimals too, but in this case it's even. So I did want to show you t-scores. So this one line of code right here for risky behavior is creating 3 different latent factors. It's using a built-in growth modeling thing where it knows implicitly that the first thing is supposed to be the intercept, the second thing is supposed to be linear, and the third thing is supposed to be quadratic. You could not do this if you wanted some other kind of change function. Doing the same thing for monitoring, but only having linear change. Then the rest of this looks a lot like what we had before, where we have fixed effects right here, random variances right here, all the various covariances, and effects of attitudes as well. One thing I forgot to mention, the observed variable intercepts have to be shut off so that all of their information about their means is pushed up to the latent variables, and I've also constrained the residual variances left over to be equal over time. That's consistent with the other model. P-width right here means pairwise width. That's how I get concurrent residual correlations. So risky 12 with monitoring 12, risky 13 with monitoring 13, and so forth. And then I made the 3 correlations that I care about here for completeness with the other output. And a lot of output later, I get the exact same thing. This is the exact same model. So what the rest of this handout does then, step by step, is change pieces of it and show you what happens. And I knew at this point we'd all be really tired, so I made sure to highlight the stuff that's new, so we don't have to go find it. So since we are out of time for today, I will finish the rest of this handout in a video and post it on the website. But I will be paying attention to the changes that I make in the code and then the corresponding changes in what happens in terms of what you get back. So for instance, the first thing I'm doing is changing 2 of the covariances to be directed slopes, and then changing, doing the same thing in SEM, and then changing the level 1 relationship to be directed from a covariance and so forth. So several iterations of that model later, so we can walk through that step by step. And then I also have, if you're interested in doing a structured residuals cross-laggy thing, that's on page 14. So this is the structured residuals version of the multivariate growth curve model. And then the lagged version in multi-level SEM as well, doing the same thing. So that's that. I will get that video recorded probably tomorrow, and I will post it on the website. All right, 143. Any questions before we call it a week? Yeah.
Yes, I have one. Page 5.
Page 5.
Yes, because this is related to the correlation between the residuals.
Yes.
Because there you have this formula, which is the covariance times the standard deviations.
Mhm.
But if we're using an R matrix that assumes no covariance between both residuals at level 1, how can we compute that thing? I mean, between risky and MON3, we are computing that RESCOV with the width, that's a covariance.
Yep.
But in the R matrix, we will have 2 variances with no covariance between them.
So the R matrix in these models is, you can think of it 2 different ways. Like, if you go full multivariate, then it would be like however many occasions for risky, however many occasions for monitoring, and then you have a whole bunch of potential covariances. And what this is doing is only turning on the one that's for the 2 residuals at the same time, and the rest are set to 0. In the SAS code that goes with this, I drilled the R matrix down into just that little like corner of it as a block diagonal structure. And so it's actually, the R matrix is per person per occasion. So then it's just a 2 by 2 matrix, because it's that occasion's residual for both variables, and then that gets a covariance. And because I've specified it that way, it's assumed to be constant over time. So if you needed to have residual variances that were different over time, or residual covariances that were different across occasions, this would not do it for you. You would have to, let me see, which one is this? You would have to do it as an SEM, so that you would have access to all of the like separate boxes to have different residual variances and different potential covariances. All right, other questions? Okay, then thanks, yes? Question or
Page
stretching?
two, hopefully
Quick, okay.
Page two.
Page
So
two.
This is the covariances only, model, this first
Yep.
one we're looking at.
Yep.
So, if we wanna know, if we wanna calculate our, like, 95% confidence intervals in the way that you taught us
Yep.
last semester, do we just take, to understand, like, average rate of change over time, how people differ, do we take the values for R-lin and M-lin in the intercepts output of the T model right there?
Yep.
And then plus or minus, the, yeah.
Plus or minus the square root of those
Square root of
things.
those things.
Times 2, or 1.96 or whatever, yep. Yeah, and so then it's like, if you have then you'll know that like what low means is either a weak positive slope or a negative slope. And that will help you interpret the results between the change factors. All right, then I will see everybody next week at 12:50 on Tuesday. Have good weekends. Let me know if you need anything. And work on your formative assessment for Monday if you haven't already done it. Bye. Thanks for being here, Zoomers and Roomers.